36 can be written as 1 times 2 to power 5 plus 0 plus 0 plus 0. No, 1 times 2 to power 2 plus 0 plus 0, right? So this is 32 plus 4 is 36. So we have 1 0 0 1 0 0. So this 36 is exactly what we have here in binary. Do you agree with this? Okay. Any questions? Okay, so that was what we did last time, and I'm repeating it. So let's see how you go with this question. Similarly, opposite to addition is subtraction. So can you subtract a smaller number from a bigger number, please, and see what you get? So we're going to subtract that. So my answer is turning out to be 10111. I might be wrong, but you just have to check whether you agree with this or not. Which one is 16? Yes, correct. If you got the same answer, then I think you have practiced these questions. If not, then you need to practice more.
It's weird because you go on the app on the LMS and on the phone it can only show so many pages. It's weird. It would just show up, it won't go no further.
It would.
I tried to connect the iPad, this is an old iPad, and it wouldn't connect. And
no, phone would be the same as a computer. Because there's not much difference.
yeah, it is. It's just it won't go down so it would only go so far. It won't go down further.
So, alright, so this is how you subtract. Your answer should be 10111. And now, based on that exercise, calculate this difference. If I was you, I would put this up there, 1, 1, then 0, 1, 0, 1, 1, and I would simply subtract it, 1, 0, 0, 1, and 0. So it's basically 1001. This is my answer for this question. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 0 is 0. So till here it's okay. Then after that I want to subtract 3 from 4. You know. So 1, 1 is 3. 1, 0, 0 is 4. So 3 from 4 should be 1. 0, 1. So this is what I have. So in other words, subtracting 1 from 0 is not possible, so I have to take 1 from all the way from there. So that is 1, 0 minus 1 is 1, but here it reduces to 1, 1 minus 1 is 0. So you have that. Anyway, well, let's move forward. for binary multiplication, the basic table is very simple. If you look at the binary multiplication, the table would be you're multiplying 0, 1 with 0, 1. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0, of course. Then 1 times 1 is 1. Yeah. So that's the extremely simple table. However, if you have a bigger table, like put more zeros, 1, 0, 1, up to so on, 0, 1, 0, 1, whatever you want to do, it would stay the same. Yeah? So 0 times any number is 0, 1 times 0 is 0, and 1 times 1 is 1. That's the only possibilities. You always have to keep in mind that you're only allowed zeros and ones, nothing else, and it would actually simplify things a lot. For instance, if you're dealing with the division, that would even simpler. Okay, let's look at some questions. So let's use binary arithmetic to calculate this this number, how it would work. Okay, let me remind you how you did the multiplication, long multiplications like this, let's say. How you did that. You started off by multiplying 3 with all of this string. So 3 times 2 is 6, 3 times 3 is 9, and 3 times 2 is 6 again. Okay. Then what you did, when you are about to multiply the second digit, what you do, you cross off first item, and then you start from the second. 1 times 2 is 2, 1 times 3 is 3, 1 times 2 is 2 again. Yeah? And then what you do, you add them up. 6 plus 0, this is 0. By cross I mean it's 0. 9 plus 2 is 11, and 6 plus 3 is 9 plus 1 is 10, and this is your solution, right? This is how you do that. It's just a reminder. Now if we want to do this for binary, what you would have 1, 0, 1, 1, 1, multiply with 1, 0, 1, 1. Now we want to multiply them. Now you can see that there are only two possibilities when I'm multiplying. Either my answer would be 0 or 1. Yeah? So 1 times this value is 1, 1, 1, 0, 1. Agree? And then I would start with 0, but the first item always goes to 0. And that would be, everything would be 0, 0, 0, 0, 0. Yeah, of course. And then you start with this number, the third digit. You would have, now you have to cross off 2 zeros because you are multiplying the third digit. And then you start from 1. You would have 1, 1, 1, 0, 1. And now when you multiply with the last fourth digit, now when you're multiplying with this fourth digit, so you would have to cross 3 zeros here, okay? And then again, you would have 1, 1, 1, 0, 1, and now you're going to add them up. Yeah? Do you agree with this? So again, the same procedure. 1 plus 0 is 1. 1 plus all zeros is 1. 1 plus 1 is 1 plus 1 is 0, and your 1 is carried forward here. Yeah? Now 1 plus 1 plus 1. Yeah, 1 carry 1. So it's 11 actually, in other words, 1, 1. And then again you have this little one up here. Now, 1 plus 1 plus 0 plus 1 plus 1. 1, 0, 0. But I'm only allowed to add 1, put 1 digit here. So the first digit goes there, and then this 1, 0 carry forward. Okay? 1, 0 plus 0 plus 0 plus 1. What is that? 1, 1. Yeah? And then 1 carry forward. 1 plus 1 is 0 again, and 1 carry forward, and that's your solution. Make sense, everyone? Okay. So here is your solution with a more sort of neat writing. This is how it goes. May I ask you to do one exercise for me, please, before we move forward. Can you multiply these two and see what you get? So this is my answer. Now keep in mind there, when I'm multiplying by 0, there is no point writing this row. There is no point writing this row because it's not contributing anything. Do you agree? Yeah? So even if you write it directly, that you have 1 0 1 1 0, and then this term which is 0 0 0 1 1 0 1, and add them up. That's it. So you can skip those two rows if you like. As in this, as here, you can see the second row is missing. I omitted it. Because it was multiplying with 0, it doesn't count. However, when I'm multiplying with the third digit, I have to put these two zeros over there because I'm multiplying with the third digit. So my starting point is shifted to after two digits.
So if it's got a 1 in it, that means that I can't, but if it's all zeros, don't worry.
Yeah, don't worry about it. Yeah, but then don't forget to replace values there.
That makes sense.
Anyway, so the answer should be 110 111 to the base 2. Don't forget to write base 2 that to indicate that it's binary, not the other ones. Okay, any questions? Now let's look at division. How division would happen. For instance, what I want to do, I want to multiply with this number. Yeah. I have not explained the method yet. I want you guys to think about it. See how the division works. Right? Do you remember long division? Yeah? Look, I have not explained the method yet, so I won't judge you. I just want to see how intuitively you think about it. There's nothing wrong about that because I have not explained the method. So the long division works like this. So let me write it down first, long division. Suppose you want to divide 32 over 6. Let me make it 320. And you want to divide on 6, right? What you think of first? First you try to divide 6 on 3. Not possible, right? Then what you do, you try to divide on 32. And see how many times 6 goes in 32. It goes 5 times, right? So you would write 30 here and then subtract. 32 minus 30 is 2. Okay? This remainder would always be less than 6, right? The quotient. So what you do next, you bring this 0 down, it becomes 20. And you divide 6 on 20. How many times 6 goes on 20? 3 times. And what is your remainder? 2 again. Now, I would not stop there. I would express my answers after that in decimals. I would add point here, point there, and add extra zeros. Yeah. So I got 20 again. So again 3. Again I got 20. Again 3, and the process continues. Yeah. So I would stop after 2 decimal places or 3 decimal places. So this is how you've been dividing, right? Long division. Can you do this process for binary? So the same way, let me give you, what's the question? It's 11101. Divided with 110. Okay. Now, I can't divide it on 1. I can't divide it on 11. I can't divide on 111. I can divide on 111, right? And remember, I'm only allowed zeros and ones. So either this number will be multiplied with 0 or it will multiply with 1. That's the only possibility. Do you agree with me? So it is actually a lot simpler than this division. Here I'm thinking of all of those numbers, right, which mostly are smaller than 6, 5, 3, all the possibilities, right? Here, there are only 2 possibilities, zeros and ones. Things are a lot simpler there. Now, can you do that? See what you get. Binary, yes.
What do you get that? Is that one model? It's a free one.
Yeah. No, you have to go off the next one. Okay, let's see. Go. A little bit. Why? A little bit. A little bit. remember doing it. Unfortunately, this is different to other sciences or other studies, in other words. Anyone else? Okay, look, I can solve these questions 1,000 times, not a problem. You will not get it until you do it yourself and keep doing them. There is no other way of learning. In teaching maths, I'm just a facilitator. I can explain methods in simple words. In the end, you have to do it yourself. There is no other way. This is technical. In technical sciences, you learn by doing things. Okay, let's do this question. 1, 1, 1, 0, 1. I want to divide it on 1, 1, 0. Okay. Now with the division, I would choose, I cannot divide on 1. I cannot divide on 1, 1 because this number is bigger. I can divide on 1, 1, 1. 1, 1, 1 is bigger than 1, 1, 0. So how many times it will go in there? One time. Okay. So you would have 1, 1, 0, and then you subtract. 1, 1, 1 minus 1, 1, 0 would be 1 only. Okay. Then you bring one digit down, 0. Can 1, 1, 0 divides on 1, 0? No. If not, then 0 goes up. Then I bring this one down, it becomes 1, 0, 1. Can I divide 1, 1, 0 on 1, 0, 1? No, still not, because 1, 0, 1 is smaller than 1, 1, 0. It's like you have 5 here and 6 over there. You cannot divide 6 on 5. So then what I do afterwards, I would put dot and I would add extra zeros. So remember, when I could not divide on 1, I mean 1, 0, 1, I have to put an extra 0 there. Okay. So what I did, remember, so firstly, when I subtracted, I had 1. Then I brought this 0 down, okay, and try to divide it on 1, 1, 0. I couldn't do it, so I have to put this extra 0 up there. Then I brought this 1 down. Can I divide it? No. That means I'm going to put 0 up there. If you can divide it, put the number by which you divide. If you can't divide it, you have to put 0 up there. Right? Then I bring this 0 down. Now this number is 1, 0, 1, 0. And now 1, 1, 0, definitely this is 4-digit number, that's 3-digit number. You should be able to divide. And how many times? You only have 2 choices, 0 or 1. Okay, so once, you would have 1, 1, 0. And what that would be? 0 minus 0 is 0. 1 minus 1 is 0. And 1, 0 minus 1 is 1. Okay, so the subtraction is 1, 0, 0. Now I will bring another 0 down. Right. And now, can I divide it? Yes, of course I can. 1, 1, 0. And your difference is 1, 0. 0 minus 0 is 0. Then this one goes all the way here. 2 minus 1 is 1. And then 1 minus 1 is 0. So you get 10. Okay. Now, would I stop there? No, not yet. I will keep doing until, for example, I will go to 6 bits or 4 bits as long as I'm directed to or I want to. If I'm not directed, If I get a periodicity, fine, I stop there. If I don't get periodicity, I will go to 6 bits or 4 bits, whatever I'm asked to do. So I put an extra 0, divide. No, it's not possible. I will put another extra 0. Now it is possible. I will have 1, 1, 0. And now you can see after that it starts repeating itself. And it will so on keep going. So my answer would be 100.1101 and up to so on to the base 2. So division is actually a lot simpler than multiplication. Right. So we've done this there step by step again. So please follow it and try to do more questions. You can verify them if you like by converting them into these real numbers, into decimals, and see what you get. So sometimes binary division may appear awkward, but the actual division calculations are very simple. As I described, that you're only in the quotient there are only zeros and ones. There are no other possibilities, so actually it makes work easier. Now, for example, if I'm asked to do this question, 1, 1, 1, 1, 0, 1, 1, 1 divided by 1, 0, 1. Now you can see first 3 digits, choose them, and there it will go how many times? 1. So 1, 0, 1. Okay. 6 minus 5 is 1. So, yeah. Do you agree with that, right? Okay. So then you bring 1 down. Okay. Now it's double digit. I'm dividing it on 3 digits. It's not possible. So I have to do 0. So I will bring another 1 down. Now it is possible. Yeah. So the difference is 1, 0. I'll bring 1 down. 1, 0, 1. 1, 0, 1. Remainder is 0. So your exact answer, this is equals to 1, 0, 1, 1. Now remember what we are doing. We have gone back to year 4 and 5 and learned addition, subtraction and multiplication. The only difference is we are restricted. We put some restriction on ourselves that we are not handling bigger numbers. We are only handling bigger strings of zeros and ones. The process, addition, multiplication, it's like, think of that as a puzzle. So there are some set of rules that you have to follow. In the set of rules, we are allowed few things. Okay, there are some fouls. We can't do that. Here we are not allowed. For example, in 0-1 strings, we are not allowed any other number. But the mechanism, process stays the same. Now, the other topic that we're going to do today is the computer representation of numbers, how we store them. Okay. Today we looked at binary number system and its useful shorthands like octal, hexa, and at ways for manipulating these numbers by hand. So now we're going to look at how binary numbers are stored and manipulated in computers. In a computer, integers and real numbers are handled differently. Now remember, integers like 1, 2, 3, 4, or -1, -2, -3, numbers like whole numbers, but with the negative as well, are handled differently than the decimals. Decimals means 2.1, for example. If there is a decimal, then it is handled differently, or rational numbers are handled slightly differently than the integers. So first we look at integers, how these are handled. Okay. In computer, an integer is stored in a sequence of bytes. Okay, where 1 byte is 8 bits. Basically, one box is split into 8 sub-boxes. So for manipulating numbers in the processor, 4 bytes, 32 bits, or 64 bits are typically available for each integer. Okay. 64-bit processors are more common nowadays. For convenience, however, we deal with only 16 bits here. The process extends to 32 bits or 64 bits the same way. Okay? So for our convenience, we will first restrict ourselves to 16 bits, that is 2 bytes only. And 2 bytes are the storage of an integer can be pictured as this. These are 2 bytes. Okay. So for example, you would have number here 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 0, 1, so on. Okay. How many possibilities are there? The possibilities are you can store 2 numbers here. Combined with that, you can have stored 4 numbers. Yeah? Yes, absolutely. 2 to the power 16 possibilities. You can store 2 to the power 16 numbers here. Right? Which would be 65,536 numbers. The number of different integers that you can store are 65,536 in 2 bytes. Okay. On a 16-bit, you can store that many numbers. So it can store integers from 0 to 65,535. Okay? Because now I included 0, so I would, since that many integers, different integers can be stored, so basically I can go from 0 to 65,535. But for symmetry, we have to include the negative numbers as well. So if this is my range, what I can do, so here is 0, here is 6535 or 535, yeah, that many integers. What I would do, I would shift my 0 somewhere here and would have numbers from the negative end as well. So what I would do, I would go, okay, so what I would do, instead of considering 0 to 65,000, I would take negative 32,768 to 32,767. Altogether, these are still at most 65,536 different integers. So on a 2 byte, on 16 bits, I can store at most that many integers, or in other words, if I include negatives, my range would be negative 32,000 to positive 32,768, 767. That would be my range. Or in easy way, this is basically what we did. We split this into, since this is 2 to the power 16, I would do that 2 to the power 15 with a negative 2 to the power 15 with the, so the range is between negative 2 to the power 15 to 2 to the power 15 minus 1. So this number is 32,767 and that number is negative 32,768. If you add them up, you will have this many. Yeah. Now, there are 2 numbers. There are 2 possibilities. Either an integer is negative or an integer is positive. So if we are storing it in this box, how to say that a number is negative or a number is positive? How would differentiate? Absolutely. So the first item will indicate that the rest of the representation is of a negative number or a positive number. Okay? The convention is, remember, when we are doing, firstly, when we are dealing with the 16 bits, then this is the range. When we are dealing 32 bits, then similarly it goes to the power 31. Okay. If the range is, if you're dealing with 64 bits, then obviously storage power increases. Okay. 2 to the power 63, humongous. It's a very big number. Right. But not beyond our imagination. Just keep in mind. Now, so how we store? The first bit is the sign bit. That is, if the number, if the integer is positive, we sign it as 0, and if the number is negative, then the sign bit is 1. Okay. And if n is whatever, the remaining 15 bits are binary representations of n, leaving zeros if necessary. We'll give some examples. And if n is negative, okay, if the integer is positive, then you have this 15 bits of binary representation. If the n is negative, first bit is 1, and after that, whatever number you have, you add 32,768 to convert that into positive number and write the binary representation of that positive number. We'll do some examples. It will be clear. However, at the end of the lecture, I'll give a shorter method, basically a brief method or easy method to convert, to represent binary of negative numbers. Okay, representation of a positive integer. Find the 16-bit computer representation of this number. Okay, so let me do it for you. First of all, it's a positive number. So let me write firstly the boxes 1, 2, 3, 4, 5, 6, 7, 8, right? So again, and another one is here 1, 2, 3, 4, 5, 6, 7. What's that? Ah, thank you. You know? Okay. Okay, so you have 8 and 8 boxes there. Now, this number is positive, so the first would be 0. Right? Now we convert that number into its binary representation. 12,723. 12,723, so I have to divide with 2. Okay, successive divisions, remember. So you would have 6,000, 3, 6, 1, and 1 remainder. Yeah. Then again, on 2, what you're going to get? You get 3, 1, 8, 0, 1. Then you get 1, 5, 9, 0, 0. Then you got 7, 9, 5, 0. So then we keep going. You would have firstly 3, 9, 7, 1. Let me know if I'm making any blunder anywhere. 9, 8, 1. So you would have 9, 9, and you would have 0. You would have 29, 1, you would have 24, 1, you would have 12, 0, you would have 6, 0, then you would have 3, 0, then you would have 1, 1, yeah? So you would have 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1. Okay, so this is my binary representation. How many digits are these? 1, 2, 3, 4, 5, 6. So let me put 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1. Okay? One box is empty. And what I'm going to do with that? 0. Absolutely. Trailing zeros. Now, storing positive integers is extremely simple. It's exactly the division we learned in the previous lectures. You know, when I said in the first lecture or second lecture that the division, although very simple that we're doing now, we're going to use that again and again and again. And this is how we're going to use again. So first and foremost, we should know how to convert integers into binary or binary into integers. Okay? And then we learn how to store them. So this 0 indicates that this number is positive, and this is the binary representation of that positive number. This is how it is stored in a computer. When you punch numbers on a keyboard, it automatically converts that into this binary representation. Questions? Okay, so this is how you have that. There was extra 0 we had to add to fill all these boxes. And we don't have to write exactly to the base 2 there when we are storing them, because then it is obvious that it goes there. Now, representing a negative number. Okay. How are we going to do that? Very similar. So suppose you have negative 7,132. Again, same way, you would have boxes. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and another box of 8. 1, 2, 3, 4, 5, 6, 7, and 8. Now, this is a negative number. 1 goes there. Forget negative now. So you have negative 7,132 plus 32,768 you add in it. Yeah. And whatever number that you get, what number are you going to get? 32,768, 7,132, you get 6, 3, 6, and 25, yeah? So you get 25,636. Yeah. So this number you're going to convert into binary and put that in these boxes here. Exactly the same way as the previous example we did. Okay. So what that would be, I won't go in that long division. I will directly write the answer here. As I said, 25,636. This binary representation would be this, and that would go in the box as all of you would have 0, 0 up to 1, 1 here. So this is the binary representation of 25,636, and this one indicates that it was a negative number. So it automatically, what it does, think of it as a negative number, and it is the representation for that. However, this is a long way of doing it, that instead of doing, here the longer way is only one step longer. What we're saying that we have to add 32,768. Suppose we don't have to do that. It will make life slightly easy, right? And that method that we're going to, is a shorthand method. We call that 2's complement. Okay, let me explain that. Negative 7,132. Just keep this number in mind. You have 1, 1, 0, 0, no. 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0. Yeah, now what I want to do, I want to convert negative 7,132 into binary. Okay? This is my representation by a slightly longer process. I want to learn slightly shorter. How you do that? Okay? So firstly, what you do, you have convert that into binary. Exactly, 7,132. Convert that into binary, see what you get. So if I'm converting that into binary, 3, 5, 6, 6, and then there's 0, and then I have 1, 7, 8, 3, remainder is 0. Yeah. So I would have then 8, 9, 1, remainder is 1, 4, 4, 5, remainder is 1, 2, 2, 2, remainder is 1, 1, 1, 1, remainder is 0. And then I have 55, remainder is 1, I have 27, remainder is 1, I have 13, remainder is 1, I have 6, remainder is 1, 3, remainder is 0, I have then 1, 0, 1, 1. Okay? So when I write it down, I would have 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 0, 0. Yeah? So the binary representation of 7,132 is this. How many digits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I have to add 2 more zeros to make it 15. Yeah? Oh, what did I do? Oh, I did backwards. Ah, why didn't you tell me before? Okay, so we would have 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, yeah? And then we had to add 2 extra zeros to make it 15, because these were 13 digits, right? 15 digits because this is 16-bit representation where first bit represents sign. Don't worry about that at this stage. Okay. Clear? So far? Just the binary representation of 7,132. Easy. Now, what we do, keep rightmost zeros and 1. 0, 0, 1. Don't change it. Exactly same. And then flip the rest. If it's 1, convert that into 0. If it is 0, convert that into 1. So you would have this one becomes 0, that one becomes 0, this 0 becomes 1, 0, 0, 0, 0, 1, 0, 0, 1, 1. Okay? This is exactly the same as that, isn't it? Yeah. So, and this 1 bit there to represent sign. So these are all your 16 bits. This is called 2's complement. So to keep the rightmost zeros, doesn't matter how many, and the rightmost 1, only 1. Don't change them, the rest of them just flip them. And you're going to get, instead of adding 32,768, you simply deal with the binary of the number given to you and then use 2's complement. Any questions? Okay. This is what I explained so far in all of this. And that's your binary representation. More examples. Find the 16-bit computer representation of negative 2,641. So remember what you can do. We can start off with, forget the negative because the first bit is just 1, it's gone. After that, look at the 15-bit representation of this number. 2641, dividing on 2. What you're going to get? You're going to get 13201, 6060, remainder 0, 330, remainder 0, 165, remainder 0. Then you have 82, remainder is 1, 41, remainder is 0, 20, remainder is 1, 10, remainder is 0, 5, remainder is 0, 2, remainder is 1, and 1 remainder is 0. Okay. So we have 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1. Yeah.